it's going.
Hello 4A, I'm trying to make some videos that should hopefully help you with this class right here. Now, you do know that you have a test coming on Monday. It'll be sent to you by email, and you have until 5 o'clock to email it back right here. Again, take a picture of it before you send it and send me the images back. It would be better if you send it back through Canvas, but if you can't get it through Canvas, I give you my email address on the test. You can email it back to my email address here rather than Canvas. Okay, so let me continue where we were when we got interrupted right here. You remember, we were just using Newton's second law, which was the sum of the forces equals ma. Really is all we were using right here. And we said that we have three different forces so far. We had gravity, which we called mg, which is straight down. We had the normal, any surface force, which is n, which was perpendicular to the surface and through the object. And we also had the tension, which is any rope, string, whatever, parallel to the surface and away from the object. Remember, our ropes don't have any weight and they don't stretch right here. So I just wanted to look at the rope again. What happens if you have multiple ropes right here? So here I have a drawing of a mass M tied to a string, which is tied to two other strings right here. Now, I don't think these are the same ropes. If they were, we would give it the same tension, but it looks like just three separate ropes tied to each other. So what do I need? If let's say I'm given M, and I want to find the three tensions. Let's call it T1, T2, and T3. Well, we'll call this one right here T1. We'll call this one, say, T2, and we'll call this one T3. Well, if we look at the forces on this object right here, what do we have? We're going down our list. We have our mg, which is right here, mg, and we have our tension 1 going up. That's it. We only look at the forces on the object. We know this is an equilibrium. The force is balanced. So if we put a coordinate system on here, doesn't matter. I'll call up positive. So if we look at use Newton's second law, we got the sum of the forces in the y direction. Upward, we have T1 minus the downward, which is mg, and that should equal 0. So we got T1. T1 is equal to mg. Okay, now if we wanted to find T2 and T3, we need something that connects it to T1, and the only thing that does that is the knot right here. There's a knot right there. And if we look at the forces on the knot, there's a T1 coming down. Remember, it's always away from the object. There's a T3 going out that way, and there's a T2 going out this way, right there. We know that knot is in equilibrium, so we know all the forces balance right here. Well, since this angle is phi, we know that that angle is phi, and since we know that this angle is theta, we know that that angle is theta. So we can break up our T2 into its component. This would be T2 cosine theta, T2 sine theta. That's the adjacent side. That's T3 cosine phi. That would be T3 sine phi right here. I don't think I'll put those in because I have enough stuff on there. So if we write out the sum of the forces in the x direction, we got T3. I'm going to put my coordinate system for this one. I'm going to draw it up here, but there's my coordinate system. We get T3 cosine phi, T3 cosine phi, minus T2 cosine theta, T2 cos theta, and that equals 0. Sum of the forces in the y, we get T2 sine theta, that's up, T2 sine theta plus T3 sine phi, that's T3 sine phi, minus T1 equals 0. Okay, so that gives me, remember I have three unknowns here, I got three equations. I know T1, I can plug that T1 into here. Now I just have two equations. I don't know T2 and T3, and we could go ahead and solve it right here. I'll let you go ahead and solve it right here. Okay, that's one case where you could get multiple tensions right here. We have another case over here where I have one rope going over these massless pulleys connected up to here, and I have a second rope right there. Here we have two masses, M1 and M2, just to make this simple. This is a smooth surface, so we'll make that smooth. No friction, right here. So now, if I write out the forces on this block right here, we have the M1G coming down. We've got the normal going up. We've got a tension over here. Tension 1, there's two ropes, so I need to put subscripts. There's T1 right there. That's it. Now if we look at the other block down here, we've got M2G, and we have another tension, T2. It's a separate rope right here. Now, since this has no friction, this thing is just going to move. This is going to accelerate here, and this is going to accelerate downward right here. So this one's going to accelerate, and I don't know if they're going to accelerate at the same rate because they're not tied together right here. So we'll call this one accelerating this one at A1 that way. Over here, we'll call this accelerating down at A2. So now we have, now we can go ahead and put our coordinate system in right here. I'm going to put my coordinate system in the direction of acceleration, which is that way, plus. We'll call up plus. Over here, it's critical. I call this way down plus. I'm assuming everything is accelerating around this way, so I'm going to call down plus. So now, if we write out the force equations on block 1, some of the forces in the X on block 1, we get just T1, nothing this way, and that equals M1A1. If we look at the forces in the Y, on 1, we got N minus M1G, N minus M1G, and that equals 0. Nothing's accelerating up. And over here, some of the forces in the Y on 2 is M2G, we call down positive, minus T2 equals M2A2 right here. Now, usually right here, if the only thing I'm given is the M1 and M2, there are a lot of unknowns here. I don't know A1, I don't know A2, I don't know T1, and I don't know T2, and I don't know N. There's 5 unknowns. I have 3 equations. I need 2 more equations right here. Where do I get those 2 equations from? Well, first of all, I need something that ties T1 and T2 together. The only thing that ties T1 and T2 together is that pulley right there. So if we were to take the forces on that pulley, we would say, oh, there's a T2 going down. Remember, it's always away from the object. You'd have, that's a T1. It's all the same rope. T1, you'd have another T1. Okay, so now let's go ahead and we'll call down positive since it's accelerating downward. So we'll call down positive on that one too. So if we look at the sum of the forces in the Y on the pulley right there, that's equal to T2 minus 2 T1s. I got 2 equal ones going up, so there's 2 T1, and that normally would equal MA. It has an acceleration, but it has no mass. Since the mass is 0, M times A is 0, so this is 0. So I do have a relationship between the tensions. I could say T2 is equal to 2 T1. Okay, there's my 4th equation. Now I just need one more equation. And that's due to the fact that the ropes don't stretch. Since the ropes don't stretch, every time this block goes down, let's say 1 foot, that means this pulley, since this is connected to that pulley, this pulley has to go down 1 foot. If this pulley goes down 1 foot, I need an extra foot of rope here and an extra foot of rope there to compensate for that to go down. But this side does not give me any rope because he's tied to the ceiling. So he has to supply all of this extra rope, which is 2 feet of rope. So this guy's going to have to move over 2 feet every time this one moves down 1 foot. So that means whatever his velocity is, this one's going to be twice the speed to give me that same distance. Whatever this acceleration is, this is going to have to be twice the acceleration. So we can say that the acceleration of this one, A1, is twice the acceleration of A2, just because my ropes don't stretch right here. Now, suppose I added a third rope into here. Suppose we had another pulley right here. And that went up to the ceiling, right to there. And we put another block here. Now, what would be the relationship between the two accelerations right here? Now we'd have 2 pulley equations, but we'd also have a relationship between these two. Again, you look and you say, well, for every time this goes down 1 foot, this has to go down 1 foot. Well, if this goes down 1 foot, I need a foot there and a foot there. That's 2 feet of rope I need. I'm not going to get any from this, so this guy's got to move down 2 feet. Well, if this guy goes down 2 feet, I need 2 feet and 2 feet, so I need an extra 4 feet of rope. I'm not going to get any there, so this one has to move over 4 feet. So for every time this goes down 1 foot, this moves over 4 foot. Whatever this speed is, he's 4 times the speed. Whatever this acceleration is, this is 4 times the acceleration. And that is what you do if you had multiple ropes. Okay. I think you had one problem like that on the homework like this. Okay.